Hello, ladies and gentlemen. Welcome to our second lecture of Advanced Statistical Modeling and Data Analysis. Last time we've discussed general ideas about Bayesian statistics, how Bayesian statistics work, and what are the main components of the model that we've generally want to create a probabilistic model of a data generating process, so certain phenomena, which for the creation of the model we will use likelihood and prior, and this will be the focus of our next lecture. However, now we will discuss how to compute quantities of interest from that probability distribution. Because unfortunately, just having the probability model is not enough. We need to do something with it. And if it's not a trivial model that is one-dimensional without any issues, then we need to address certain computational aspects of it, because unfortunately, simple computation, computation of quantities of interest in the statistical models is not trivial. Generally, we will want to generate samples from our distribution, which will allow us to estimate quantities of interest, in particular expectations of certain functions that we'll be able to compute. Having those expectations, we'll be able to, and those functions that we want to compute will not necessarily be just an expected value, but an expected value of certain functions. And those functions can represent practically anything that we really want to take from the distribution. So generally, when speaking about random number generation, we have two options. One option is hardware random number generators, and the second one are pseudo-random number generators. Hardware random number generators are really tools that are attached to your computer and provide you with potentially uncorrelated random numbers generated by some kind of physical source. Usually it is an electron lamp that generates enough noise by itself and with certain filtering creates you random numbers. In pseudo number is a bit more complicated. But generally, random number generators are used only in very specialized situations, and the most bread and butter of computation is pseudo-random number generators. A pseudo-random number generator is generally a formula that would generate a sequence of numbers, so our candidates will be random numbers, which will have low autocorrelation, so one sample will not depend on the previous ones, has a long period, so it won't return to the previous values, and uniformly distributed quartiles of the generated numbers. So those numbers will look like from the uniform distribution. The simplest way to generate a sequence that looks like that is a linear congruent recurrence, which generally is a computation. Next sample is generated from the previous sample using a linear affine transformation and a modulo operation. This, as long as we choose appropriate parameters A and C, we can get very nice working random number generator that will generate simple sums. They will have some autocorrelation, they have some periods, but generally for very simple uses, it will be enough. However, currently widely adapted is so-called Mersenne-Twister algorithm. That is a much more advanced method of generating random numbers. And we will not be discussing it too much. However, you can find a lot of information about this. Mersenne-Twister is at the moment is not the most advanced random number generator, but it's widely used, implemented in most of the probability libraries. So generally, let's focus on certain preliminaries that we are interested in. So having a probability distribution defined over some kind of one-dimensional space and having a one point in it, we can define easily an interval between a minimal value and its value, which will be the have a probability of uh, represented by the probability of the interval is we can represent as we can assign a number of what happens. What is the probability of x belonging to that interval? In case of continuous distribution, this is the only way that we can represent numbers by intervals, because each point has, as we know, a zero measure probability. Cumulative distribution function, of course, is a function that maps each number to its corresponding probability of depending of x of probability of interval from minimal value of x to the current x. The minimal value of x can, of course, be minus infinity in case of unbounded distribution. In case of bounded distribution, this is the lower bound. So cumulative probability distribution is a function that to each number assigns the probability of what is the probability of this of having a number like this or lower. Quantile function is for all what we really need is an inverse of cumulative distribution function, and it is a bit more difficult, but for practical purposes we can absolutely focus on that. This is just an inverse of CDF. And this is a very useful situation because in one-dimensional systems we can easily generate, for one-dimensional distribution, we can easily generate samples from any arbitrary probability distribution by joining the quantile function and the pseudo-random number generator. We will generate a sequence of uniformly distributed numbers, as we mentioned before. Pseudo-random number generators generate us uniformly distributed samples, and we have those samples in our interval between 0 and 1. If we are working on integers, we just need to scale it. If we want to work on different methods, we just need to this 0 and bound. And if we, to each of those samples, we assign corresponding quantile function value, then the sequence of those numbers, the values of quantile function, will be a sample from our original distribution. So just having a quantile function and pseudo-random generator, we can generate samples from any one-dimensional probability distribution. So having a sequence of samples from that distribution, then we can easily create a Monte Carlo estimator of the expected value of such function. That is, we are interested in the expected value corresponding to the probability distribution P of the function f. And function f can be correspond to actual expected values, so it will be a mean. It can be moments functions, it can be quantiles, though all of those can be represented as expectation of certain numbers. And for such computation, we can just estimate it by an average of those samples, because this Monte Carlo, if we get a sequence of samples from our distribution, then the Monte Carlo estimator, so the mean of the values of that function in the samples we've computed, is asymptotically consistent. That is, as the number of samples grows to infinity, we will get the actual expectation of that function corresponding to the probability distribution of pi. And from it is very easily to see from central limit theorem that this is approximately normally distributed, because our value of our estimator has a normal distribution that has a mean equal to the expectation and the variance defined by and the variance respect to the function of f and divided by the number of samples. And as long as n is sufficiently big, even like n equal to greater than 10, it's usually a solid number. then we can approximate the our expectation using our estimator with a probabilistic standard error represented by a variance of our function divided by n. So this normal representation for the distribution of values of our estimator is a normal centered at the actual value with variance defined, or the standard deviation defined as a was a ratio of variance of our function and number of samples. And because we want to estimate, we can estimate this Monte Carlo standard error also using an appropriate estimator just by estimate of the variance using our samples from our distribution. So we have estimated the mean, and we can estimate the also the Monte Carlo standard error. And all those values can be directly estimated from our samples using the sample means and variance. I mean the sample mean and variance, of course, of the value of the function using the computed using the computed samples. In practical situations, we might want to have consider the relative error, Monte Carlo standard error. So the percentage representation of our error, and if we want to have the Monte Carlo standard error, the relative error of our estimator, be bounded by certain sample, we can compute using our estimates. We can compute the numbers of samples that are actually needed for it to be samples that need to be needed to ensure such standard error. Unfortunately, this can lead to very large numbers. And as mentioned before, all those expectations that we really want, those samples that we obtain from our probability distribution, can be used to compute certain interesting quantities, because all those things can be represented as expectations of certain functions. So we can compute moments and cumulants, even probabilities. We can compute histograms, which histogram is, in a sense, a certain statistic. We can compute empirical distribution functions, which is a certain complement to a histogram, and we can, of course, compute quantiles. And for the purpose of the distribution summary, we can use multiple functions. And generally, most known are moments like mean and variance. Less known, but still popular, are skewness and kurtosis, that are the moments of the higher orders. And there are also cumulants, which are very similar to moments, but sometimes less used, but sometimes needed in certain applications. And those are, of course, directly computed by computing certain expectation of certain functions. For example, for variance, you need to compute the expectation of x squared with respect to original samples. For the probabilities of events, we can actually use the we are very often interested in the probability when the function value lies in certain interval of interest. For example, what is the probability that we will have a return of 10%, for example, of like between 9 and 10% of our return on our investment. And actually, this is done by the computation of the expectation of the indicator function. Indicator function, that is a function on a certain set or on an interval, or generally, depending on the dimensionality. It is the function is 1 when our function belongs to this interval or this element of space, and 0 otherwise. An expectation is estimated as usual by computing the values of this indicator function for our samples. And because this indicator function has only those 1 and 0 values, it reduces to just the number of samples in the area of interest divided by total number of samples. So this will be in our estimator of the probability of function value relying in this interval or setting. And it can be actually very easy to determine the Monte Carlo standard error of the indicator function, because the square of the indicator function is its indicator function itself. So variance of the indicator function can be computed directly from the corresponding probability, and that gives us the Monte Carlo standard error, which is in absolute form, is a typical known value from the, for example, known from the binomial distribution. That is estimated probability times 1 minus estimated probability divided by n. If we, however, are interested in relative error, things become a bit more interesting. Because, of course, the computation itself is very easy. But if the probability, the relative error is inversely dependent on the estimated probability. Because if probability is, we are considering probability of an unlikely event, so the estimated probability will be low, then our relative error is inversely proportional to that value. So as long the smaller p is, the relative error will be larger unless we increase the number of samples. So for example, if our probability of interest is 1 in 100, and we want a relative error of less than 5%, so we want to be very confident about our 1 in 100 chance of event occurring, then we need to have a sample size of greater than 39,000, which is a relatively big number of samples. And that gives us that if we want high precision about low probability events, we need to generate a lot of samples. This, of course, is logical in a sense that if something is unlikely, we would need to be very certain how unlikely it is. But still, this is something that we need to be aware of, that our uncertainty of unlikely events is higher than our uncertainty of the more likely events. And histogram is generally the idea of doing the same but multiple times. Because if we consider histogram just a visualization tool, this is of course a plot that we divide the space into, we divide our into intervals, and we compute number of samples in such intervals. So generally, we compute indicator function, we compute the counts of samples in intervals, so we can, in a way, compute expectations of the certain intervals. And that, if we look at it this way, all this analysis works here as long as we consider that our histogram is not just a property of the sample, but is an estimator of the probability distribution. Because histogram in this way can be used as an estimate of what is our probability distribution and what kind of uncertainty about this probability distribution we have from this sample and from what we have. And generally, in practice, we using the three types of histogram normalization. One is no normalization, so we just display counts, and this is just statistics of the data. This is the hardest to interpret as probability distribution. The other option is to divide the counts by the number of samples in advance. So that gives us that our probability estimates are we are approximating our probability distribution function by probability mass function. So a discrete distribution that only events possible events are just sample belonging to a certain interval. Or we can normalize it in a way that the integral of the histogram, considered as a continuous function, integrates to 1. A companion histogram is the empirical cumulative distribution function, which is, I think, the simplest way to represent what is the ECDF is just by code. Because generally, it is computed by sorting the value of x of our sample, and then computing how many time each sample occurs. If samples don't double, we just all those counts are not repeating, then all our counts are of course equal to 1. And for each value of the our function, we will just assign the number of samples that are smaller than it divided by the number of samples in total. So we just create a very simple estimate. And what is actually interesting is that we can also consider the uncertainty of the empirical cumulative distribution function when treated as an estimator of the cumulative distribution function, because in each point we are actually having the uncertainty of each interval, and those interval uncertainties are being can vary depending on each of the intervals. Of course, the idea is similar. Quantiles are kind of an inverse problem to determine the probability of the interval, and it of course is implicitly p quantile is defined as a point yp satisfying that the probability of that the p will be equal to the probability of interval from the minimal to the yp is equal to p. And generally, we get quantiles of the sample are very simple to compute just by counting the numbers of samples and dividing them by appropriate value. So just finding those number of samples, as long as our quantiles correspond to the our appropriate divisors of the number of samples. If they are not, then there's a problem that we cannot assign the given point directly. We can find some kind of interpolation between those points, and there are multiple ways to do it. It can be linear interpolation. It can be more. Kind of nonlinear interpolation. Options are limitless, depending on the implementation. However, what is again important, in case of low probability quantiles, we still have a lot of uncertainty because our probability of each of the intervals has a lot of uncertainty by itself. So the value of the quantile directly also will be strongly uncertain. So let's start with a simple example to show how it works, how those statistics works, because they will be needed to understand what's going later. So starting from a very, very simple normal distribution with an expectation of 1 and standard deviation of 1.25, which can of course be very simple generated in Python. Let's take 1,000 samples from this distribution, and as long adding more and more samples give us the Monte Carlo estimator of the mean, which is, as we expect, asymptotically convergent to the actual value, and we have those uncertainty estimates from our interval. The histogram of this sample, again, using our computation that we wanted, gives us the certain error bars happening here, which are dependent on the size of the probability of the interval and the number of samples that are happening in it, because for each of those we have separate estimates of the probability. Uh, when we take an analytical representation of our functions, so we have the normal distribution with mean of 1 and standard deviation 1 per 25, we of course see that there is consistency with which generally we should expect in 1000 of samples. Depending on, however, the problem with histogram, as always, is the selection of being, because the way we split our interval into, split our data range into intervals influences the uncertainty and quality of approximation. Because when you take a coarse binning, you see that our representation of normal distribution is very poor. It's not regular. We cannot see this normality that well, which can be seen here, but by the reduction of the width of the intervals, the probability, relative probability of each interval is more, it's given with more uncertainty. We have less samples in each of the bins. So having less samples, the uncertainty can be relatively large, which can be extreme in the sense that we get too fine binning, because then we have lots of variance in the estimates, and also we have lots of uncertainty. So the histogram can be less useful. In case of empirical commutative distribution function, here we can see that the uncertainty is well spread over the entire distribution, with the most of them located in the center, when again we have also more samples, and situation is more, let's say, more clear. Depending on our distribution, we can see that this is the sample mean here. We have the observed values. This, of course, can be used for any kind of distribution. When we take, for example, data transformation, we can compute as statistics as easily as previously. For example, if we take, let's say, an inverse logistic function, so the expit function, that is the function that represents allows us to transfer from real numbers to the 0-1 interval, then we can easily get the something that would require more advanced computation is easy to compute. So we can easily estimate the expectations. We can easily create a histogram with them, so we can estimate the entire probability distribution, which is consistent with the analytical solution that we obtained. So generally, by sampling, we can verify our analytical results, or otherwise we can verify our sampling with the analytical computation. And moreover, in some case of those push-forward distributions, when we are taking our function and using some with our distribution, and we are using some kind of complicated function, it might be much easier to just work with samples than to determine set a computation analytically. And like for completeness, we can also see the CDF of our distribution. The bigger problems, as always, are with heavy tail distributions, because in certain situations we are interested in distributions that are not normal, and that's often happens in case of being prepared for less likely events. So we need to, as we know, the normal distribution has this, let's say, limitation that events that are few standard deviations from the, like say 4 or 5 from the mean are very unlikely. And there are certain events that can happen, and we need to be prepared for that can be drastically different from the mean. And what we will work here, we will work on the we'll be working on the student T family probability distributions, which are the generalization of a normal distribution, because as long as the value of degrees of freedom here tends to infinity, this distribution tends to the normal distribution, which can be actually very useful because this can be used in place of the normal distribution in certain computation, just to allow the possibility of certain unlikely events. So we can provide it with certain robustness to outliers. We'll discuss it on next lecture. In case of student distribution, depending on the number of degrees of freedom, we can get a bit of complication, because if student distribution in this form has greater than one number of degrees of freedom, which is an unfortunate name because this number can be easily a real number and not required to be an integer, then it has a zero expected value. However, if it's equal to 1, so we have a special case which is the Cauchy distribution, it is not defined. In case of variance, as long as we have 2 or more degrees of freedom, then it can be directly computed. That is the degrees of freedom divided by degrees of freedom minus 2. And if we have between 1 and 2 degrees of freedom, the variance is infinite. And if we have less than one or less, then variance is as mean, it is undefined. And sampling for it is actually very simple because we can generate samples from, let's say, Cauchy distribution just by assigning 1 degrees of freedom to a standard T distribution from nowhere. And as we said, Cauchy distribution has undefined mean, and trying to estimate it gives us this problem that for certain periods of time we can generate rather well-behaved samples, but once every while we get a jump in the value because the unlikely but possible number that's very far away from zero can happen, and it can completely disturb our estimate of the value of the sample mean and completely disturb our estimate. So for undefined expectation, we have a big problem of getting getting absolutely unreliable estimator, which makes sense because this value does not exist. And increasing the number of samples will not improve the situation in any way because it's always will be disturbed by those samples coming from the tails of the distribution that will disturb the sample mean estimator. And so does the central limit theorem even hold in this case? Because we were using central limit theorem to justify our samples from the behavior of our estimator that generally is approximately normally distributed. It's centered in the expected value. And if we tried multiple times, so we will get multiple samples and we'll try to analyze the histogram of the estimator. So we we're getting multiple samples from our Cauchy distribution, and for each we'll try to estimate the the expectation. We can compute the histogram of it, and as we can see, it is obviously not normal, and it's not normal because the expectation, of course, does not exist. However, it is very important that while we cannot compute the mean of this distribution because it does not exist, the probabilities are generally well defined. So if, for example, we are interested in the estimate of probability of sample belonging to an interval between -1 and 0, we can easily estimate that probability using the same methodology as before. And in this case, there's no problem because probabilities are well defined. What's not defined are the moment functions, which are not a big problem in this case because if we want, the same is with quantiles and other stuff, all those things are well defined. What is not defined is the mean in a traditional set. And of course, we can compute those errors easily because we can compute the estimated value from the Monte Carlo estimator, and we compute the Monte Carlo standard error, which is also very well quantified, because in case of these functions for each values exist, there is no problem with the existence or the working of central limit theorem. In cases of infinite variance, we have a similar situation, but slightly different. So when we increase our degrees of freedom to 1.5, so between 1 and 2, we can see that we have the mean estimated, but the uncertainty around it varies, and varies independently of the number of samples. And again, the under quantification is unreliable because our estimator is not normally distributed around the mean, because the variance of the function does not exist, and our estimator relies, as we defined it earlier, on the value of variance. If variance is undefined or infinite, then we cannot compute it directly. The estimator of the variance will not work, and in consequence, the Monte Carlo standard error estimator will also not work for such computation. And if we increase the number of degrees of freedom above this magical number of 2, then there is no problem, because estimator behaves reasonably, and the estimates of those functions are relatively simple. And of course, the errors of the estimator behaves normally, and we can confirm it, the set limit theorem. Generally, what we have here is called tail behavior. And tails of the probability distribution, that is the areas far away from the mode, from the mode or the median of it, so the central, generally some kind of central value, they are called tails. In case of Gaussian distribution, normal distribution, those tails are very less. It's called thin, and thin tails mean that the events happening far away from the central value are highly unlikely. However, distributions such as Cauchy or generally student distributions are heavy-tailed, are not only those. And unfortunately, in many cases, even our collection of our distributions coming from normal values can also result our Bayesian distribution of our quantity of interest can also have heavy tails, and analysis of that behavior is important. And one way of it is using a special distribution called Pareto distribution, which is a very traditional, typical heavy tail distribution, which has a so-called power law. So its probability behaves like a inverse of the power of an inverse certain value. So it's like a power less than 1. And it can be a good model for extreme values, and it's very useful for diagnosis of our samples, so to verify if our samples can be heavily tailed. And for that, we can even use classical statistical estimator, which is a point estimator, not a Bayesian estimator, but a frequency estimator, just as a statistical check for our problems. And fitting k for the tail of each distribution, we can estimate the parameter of k of Pareto distribution, and that gives us a certain diagnostic tool. As long as estimated k will be less than 0.25, there is no problem. Those distributions are not problematic, their tails are well behaved, those samples will not issue. If k is above 0.7, then usually we have very heavy tail distribution that requires certain care in analysis. And this can happen not only to the values of, of parameters, but generally some kind of statistics that we are interested in. And one of the method of verifying this behavior is just we split our distribution into its tails. So we take a central value, for example, using median, and then we define the values that are at least one median away from the distribution, and we then compute the k-hat for left and right tails. So those behaviors that are at least one median away from the center. And considering our previous examples, we can see that for Cauchy distribution, k-hat is really problematic. It's big. It's above the threshold that we mentioned, and of course, depending on the number of samples, we can get better or less estimates of k-hat, and we can see that all of those are greater than 0.7 Cauchy distribution. In the case of 1.5 degrees of freedom, student distribution can behave above this threshold that we wanted, below 0.25. It's not the most terrible, but we've seen it's problematic. And for 3 degrees of freedom, then k-hat is very nice, it's close to 0. And no issues happening. For normal distribution, it's even negative because our distribution vanishes very quickly. So as we can see, it's a not problematic situation. So generally, as long as we can get our what we really need to think about it is that Monte Carlo methods allow us to sample from certain distributions and get information about its behavior. And as long as the distribution is not too crazy, or at least the distribution of statistical interest is not too crazy, we can get good estimates and error quantification. Of course, each probability estimate has its own error, it's called Monte Carlo standard error. And we need to be aware that our samples are not our statistics derived from our samples have some problems. Those problems are normally distributed, and in most cases, and inversely proportional to number of samples. If distribution is problematic, doesn't have enough moments, there might be issues that we can be generally diagnosed in certain way, for example, by analyzing detailed behavior. Unfortunately, all those things from direct Monte Carlo computation work very well for unidimensional distribution. In case if you have more samples, more dimensions, then we have problems. And we need to use more tools, which is the main bread and butter of computation, which is Markov chain Monte Carlo methods. For extra reading, we can look at the work of Michael Betancourt that I mentioned before. He has a very nice, more detailed analysis of behavior of Monte Carlo sampling. For the k-hat estimator, there's work by Zhang and Stevens, which is a very good diagnostic tool. And for Mears and Twist, it can be found on Wikipedia very well described, and there's also there's also, of course, a reference paper that you can check. But as I said, that will work for the one-dimensional case. In case of more dimensions, we have problems because, as we said, from one-dimensional distribution, we just took a random number generator, and from this random number generator, we sampled the values and used the quantile function to determine the probabilities. For more dimension, for more greater number of dimensions, we have problem with existence of quantile function. And generally, we need to find a way to generate samples from our multidimensional distribution. And here, for the rest, we come Markov chain. Because Markov chains are the processes that, with certain probability of points moving through a certain multidimensional space, that assign the probability of transition from one point to another in the space, they assign certain probability that is conditional on the value of the point that we are now in. So Markov chain is a method of wandering around a certain multidimensional space with certain probability of moving into certain points. The most simple example would be in a two-dimensional space would be the movement in the dimensional space, when our movement in each of the axes, each of the dimensions is independent on each other, and generally is normal depending on the parameters, its own parameters. For simplicity, we assign a common standard deviations for all those. We just have a normal distribution moving from one of those individuals. This can, of course, be very simply computed by using the random number generators, and we can generate from one point, for example, point 0, 0, assuming that we have a standard deviation of 1, we can assign the probability of movement from point 0, 0. We can see possible transition from this point. So we have the 50 possible transitions that can happen here. Each of those has probability described by the normal probability distribution in each of the axes. However, only one transition occurs depending on our other generator, so it moves from that point to another. So of all the possible transitions, we just move from point 0, 0 to this new point. And again, when we move to a new point, we have generally again new possible transitions governed by by the normal distribution where we can move, and of course next transition occurs, and so on. So in our multidimensional space, using sequence of Markov transitions, so moving from point Q0 to point Q1 wave Q wave 1 with using the transition defined previously, then which depends only on location of new parameters and the previous one. Again, we can move to all those sequentially. So we have a sequence of points in the space which we call Markov chain. And so what? Why we are interested in that? We are interested in that because the Markov chains behavior have something called, as long as we have certain assumptions fulfilled, the Markov chain can have something called a stationary or invariant distribution. This is a distribution defined as such given expectation that such integral of that distribution and the transition probability divided by Q prime will give us the probability of interest of Q. So that really means that the Markov chain will wander around the stationary typical set that is concerned with that is connected to our unique stationary distribution. So as long as Markov chain has certain assumptions fulfilled, it will have a unique stationary distribution, and our samples from our Markov chain will be wandering the stationary typical set of the distribution. And that gives us the bonus of having samples from that distribution, which after reaching the typical set will be exploring around it. And as long as we are getting the samples from the typical set, which we explained last time what the typical set is, we have the estimators, Markov chain Monte Carlo estimators, which are very unlike to Monte Carlo estimators. And as long as the Markov chain of interest are irreducible and recurrent, we have the asymptotical consistency as previously. But because we are generating samples, we'll never have infinite number of samples. We have a finite number of samples. So in the ideal case, first we will reach the typical set. Then we will explore it, approaching the value of interest, and then by moving around the typical set, we'll get samples that are close to the asymptotical. However, problem is that the more complicated distribution, the more complicated typical set can be. And it can have a very difficult geometry to explore. Just similar to the optimization, we have a complicated geometry of indicator functions that you want to minimize. That's, for example, well-known banana valley, that the area of small gradient can become very complicated to move around. And in case of exploration by Markov chain, the typical set, we can have some places that it will be difficult for the chain to move around because the probability of movement in it will be very complicated. And it unfortunately can work that our initial exploration will be rather okay and nothing bad will happen, but our complicated shapes might cause a situation that our samples from our Markov chain will be constrained by the shape here. So they will be all located in this difficult place and it will introduce biases. Which even if we leave this complicated area, we still have a biased estimate. It can be even more complicated in the multimodal distributions when sometimes chain can be just drawn to one of the modes and will not explore the other one. So we will not approach the real actual expected value, which will be somewhere here because we are just around here. And even and the problem is that it can be difficult to diagnose because if we didn't know that there are two modes, only after very long sampling that sometimes the sample will reach the second typicals. We have, of course, the analog for quantization of errors, which we call a Markov chain Monte Carlo central limit theorem, which is similar to Markov chain, to Monte Carlo central limit theorem for estimators. However, the standard error is defined as division of variance of f by the quality called effective sample size. And effective sample size is the measure of how the Markov chain is autocorrelated with itself, because it computes the number of autocorrelations that we have. If Markov chain is completely not autocorrelated, then of course effective sample size is equal to n, which is a big benefit. So even using the estimated values of the effective sample size, we can easily estimate the. Sorry, if we are using estimators of autocorrelations, we can use the compute the estimator of the expected sample size using the sample variance and fin sums of those autocorrelations. And of course, as I mentioned, if all samples are independent, then autocorrelation will vanish and effective sample sum is equal to it. If autocorrelation are positive, then unfortunately effective sample size will be smaller than n, and that will increase the Monte Carlo standard error. That really means that samples that are Markov chains that have difficulty exploring distribution can lead to less reliable estimators. In certain situations, we can also observe negative autocorrelation, which can enhance the effective sample size. And that is the issue that we have the that can actually be beneficial. Unfortunately, it is unreliable to create the Markov chains with the negative autocorrelations. It is hard to create those, and it won't work in all cases for quantities of interest. That's why it's not a reliable method to improve the estimates. So we can, of course, estimate our errors using the estimated Markov chain standard error by division of sample variance and estimator of the effective sample size. Generally, what we want from our Markov chain is stationarity. That we want to see that they will start exploring the typical set, which we can observe on the so-called trace plots. In those trace plots, we can also diagnose certain problems. For example, defreezing, the situation where our samples are stuck in center point and new samples are very closely related to each other. If our samples Markov chains are too short, we might not observe this situation and we not know there's a problem. And unfortunately, it still will be unreliable. The biggest problem with this is that we can observe only marginal trace plots. We cannot observe the trace plots in the entire parameter space. So we might not capture problems that are multidimensional in a sense. Because we have there's possibility of multimodality, those we can observe stationarity but in separate modes. So that is why we need to use multiple chains to get some kind of information about the behavior. And we can use it with detection of multimodality. So if we initialize our chains in different spaces, we can get more information. And also they can capture other situations, for example, the freezing that might not be observed for one initialization but happens in another. And having more chains, we can of course use certain additional diagnostics. For example, we can compute within chain variance, so we see how the chains are happening, what's happening in chain. We can get between chain variance, so how each chain differs from each other. And from that, we can use the R-hat estimator, which is called potential scale reduction factor, which generally says that if all mark within chain and between chain variance is the same, then it is good situation because each chain explores the distribution the same way. And that gives us the and in such case the R-hat is equal to 1. This of course is still a marginal statistics for each of the variables of statistics of interest. So if it cannot might problems capturing certain aspects that are multidimensional in a sense. There are also different statistics like a Gewicki statistic, which is a comparison of estimators from the beginning and the end of a single Markov chain. This is less used. There is a split R-hat, a variant of R-hat that is generally works this way, that we take the samples, the chains, and we split them in half. And each of those chains we treat as two shorter chains, and we then compute for all of those. So that gives us possibly more information on the behavior within chain. Also, there are certain computational methods of modifying R-hat to avoid certain heavy-tailed problems that is used by certain rank statistics. Either way, there's a problem that we mentioned before, that all this part works nice if we are in a typical set. And when we reach the typical set, all the samples are variants. However, how long it takes our Markov chain reaches a typical set. And theoretically, we could use just after initialization, but it can introduce biases. We can use some kind of adaptation. That is, we use the information from the chain by itself to see how it behaves, that we can say, okay, we are now in the typical set. Or the most practical approach that is being used in multiple statistical computation software is use certain heuristic methods to just drop certain number of iterations. By default, for example, in STAN or PMC is 1000 iterations that is dropped and 1000 iterations that are used for computation. And how to find a Markov chain with desired stationary distribution? For the most famous method that is was described as one of the most important algorithms of the 20th century is the Metropolis-Hastings algorithm, which generally relies on the following assumptions. It relies on the assumption that we can compute our distribution of interest, or at least its numerator, and we can generate samples from some kind of distribution in the same dimensional structure. For example, normal distribution. We do not know how to generate samples from pi, so the distribution of interest, because we can't. Because if we could use just Monte Carlo estimation directly. No, Markov chain would be needed. But we can compute its value. And the idea is that we generate a possible transition from one point to another using our easy known distribution. And then we compute something called acceptance probability. And acceptance probability is the minimal value between 1 and the fraction of value of new proposed value at the distribution of interest divided by the previous value, and the dependence of our proposal distribution probability from moving from new point to the previous one divided by the probability of previous one to the new one. If it's a symmetric, then of course this cancels. Then we either accept this transition depending on this probability acceptance. So we generate a random number and we decide, depending on its value, we decide either we move or we stay. If we go above threshold, then we move, below threshold, then we stay. And well, in case of so-called random walk metropolis, we just use normal distribution for transition probability. We can use also different distributions. So let's start with something very simple. Let's take a let's take a normal distribution. In this case, we take a normal distribution defined in form a logarithm. So we just take a logarithm of the distribution, which makes our computation simple. And of course, our normal distribution has those contours of probability that we can easily compute. And we'll generate transitions in using the normal distribution. In two-dimensional case, we generate appropriate samples, and we have our Metropolis algorithm that generates our samples using, as you can see, the division aspect. Why we did it like this? Because when we use the probability distribution logarithmically, we don't have the problem that when we are, for example, in normal distribution, too many sigmas away from the mean, those values of distribution function are very, very small. And in case when we instead of dividing those two by each other, we just exponentiate the division of logarithms, the difference of logarithms, and that allows us to avoid rounding errors. If the result will be very small, then the exponent will be, of course, the probability will be very small. However, if they're close to each other, but small individually, we can still do a transition which will be rounded down to 0 otherwise. So just accept a method of avoiding a situation. We save the acceptance probability and we just accept it based on the random number. Okay, sorry, because I didn't add a proper report. So we can compute from our samples, we can compute variance, first and second variables, we can compute its statistics, splitter hat, estimated sample size, and Markov chain standard errors. So we can compute our values, which are consistent with our distribution because our distribution had modes mode at 1 and -1, and this can be observed here that we have this asymptotic convergence using the observed 5,000 samples. In case of more complicated distribution, like here, we have a two-dimensional distribution that a multimodal distribution, which will be a mixture of two normals with the different means, but the same standard deviation. Oh, sorry, I think I've dropped some slide here. Wait a second. Okay. Okay, this shouldn't happen. This just shouldn't happen, and that will be enough. But unfortunately, it did. There's some kind of artifact of. So generally, that was this was the kernel density estimator of our. Okay, sorry again. This should be actually a stat, and that should be enough. Okay, so moving from our distribution here, we have in a two-parameter space, we can see that it behaves like this. This is a kernel density estimator of using the sample. Let's take a second sample, which will be a bit more complicated sample because it will be more dimensional. That has a complicated geometry. This geometry is actually behaving on the scale of. It happens like this, that this distribution has the standard deviation that is dependent on the first variable. So first variable is like first variable decides the scale of the other variables, and it gives us contours like this. So we have a very complicated situation depending on the number of contours. In this case, this will be a 10-dimensional system. We get a very complicated shape of our distribution. But the metropolis distribution works exactly the same. We just need to provide it with a computation of logarithm of desired probability function, and the estimates look not very nice. We can see that our variables can have a large standard errors. You can see a very small estimated sample size. And we can see that our estimators do not converge, and this is caused by the complicated geometry. Okay. And then we'll make another third example when we create a mixture of two normal distributions centered, one is centered at point 4 and 1, one with mean 4 and 8 with no uneven standard deviations, and the other one centered at -8 and -4 for each of the variables, and we just create an even mixture of those distributions. So it looks like this. We have equal probability of being here and here. Again, the algorithm looks exactly the same, just replacing the probability distributions in the metropolis Hastings algorithm. We can get some information and our chains just look reasonable. But the behavior of the distribution is that we are just started here during the warm-up, and then we started exploiting only one mode. If we increase the number of transitions, then things start to change, but the Markov chain standard error rises, the estimated sample size is very small, error hat is huge, because we had a jump here. We had a multimodal distribution, and this is a problematic situation that after starting here, it moved to here. So we had a transition moving from here. Conclusions. The Markov chains Monte Carlo methods are the base of our computation. We've discussed the most simple method, that is the Markov Metropolis-Hastings method. In practical computation, now we use much more advanced algorithms that in one or more ways enforce the exploration of our probability distribution. One way is the more traditional way is so-called Gibbs sampling, when we, as long as we can compute the marginal distributions of each of the variables conditional on each other, then we can sample those individually in a sequence. That can be very difficult for more complicated models. At the moment, state of the art is Hamiltonian Monte Carlo method, which constructs the Markov chain using certain differential flow using the curvature of the probability distribution. In such case, it requires more computation. It requires online solution of differential equations that are being created by automatic differentiation of the probability distribution. But it can explore functions very well, and those examples we'll see on the next lecture. In case of the probability distributions for the different methods, we can also use methods that are reliant on approximating the probability distribution in certain sense, usually using Kullback-Leibler divergence, using some simpler distribution that we can sample from. This is so-called variational inference. There are methods based on avoiding the likelihood and simplifying the model directly just by computing certain statistics. This is called approximate Bayesian computation. It is very unreliable for normal cases, but sometimes solution for only for certain. And there are certain methods based on Langevin dynamics that can be attractive in certain cases. Okay. What are the questions at the moment? If there are any questions from those people who are watching, I will give it a 30 seconds or so. And if not, the next lecture will be next week, because we need to catch up with the topics that will be being covered, and we still need to do at least 2 or maybe 3 lectures. See no questions, so thank you very much and have a nice day.